Alright, so for the seepage analysis, here we are interested to find out about the seepage line and where it is going to exit the dam on the downstream. So for safety of the dam, we want to make sure that the seepage line is well within the downstream phase of the dam. So the seepage line should not be passing through the downstream phase. And in the seepage analysis, we have some assumptions that we make. And the first is we assume that the water is flowing because of the hydraulic gradient, meaning you have a head difference. So let's say this is the embankment here, and this is the upstream water. Then whatever the water is seeping, we assume that because of the head difference from upstream to downstream, the water is being driven. And since the water is flowing through soil, we assume that the Darcy's law is valid. And then we also assume that there is no change in the degree of saturation of the soil. And the continuity equation is valid, meaning whatever the volume of water is entering must leave. So that is the continuity equation. And then water is incompressible, meaning the density of the water is not changing over time. So the density is constant. Now the seepage analysis and the flow through the seepage lines, we calculate based on the Laplace equations. Laplace equations are the flow equations in 2 dimensions when you have a head difference and the potential. So let us say we assume a small element, soil element, and then the water is entering this element and exiting. Similarly, the water is entering from the top and exiting from the bottom. And let us say the velocity that comes in is Vx. So the velocity of the water that is entering this element is Vx, and the gradient of the velocity is dou v by dou x. So the change in velocity is dou v by dou x, and since the fluid is traveling a distance of delta x, then the new velocity would be Vx plus dou v by dou x multiplied by dx. So we have an entry velocity of Vx, and then we have an exit velocity of Vx plus dou v by dou x delta x. Similarly, if we have a fluid that is passing from top to bottom, then the velocity in the y direction is Vy, and the velocity gradient or the change in velocity is dou v by dou y, and the change is occurring over a distance of delta y. So the new exit velocity would be Vy plus dou v by dou y multiplied by delta y. So this is our original inflow velocity, and then this is the change in velocity, and this change is happening over a distance of delta y. So that is why we add Vy with this term. So now we know for this small element, we know the entry velocities and exit velocities. And we also know the cross sections. If we are considering per unit length or unit width, which is into the paper, then we can apply continuity equation for this element. The continuity equation is area times velocity. So we have velocity multiplied by area, so which is Vx, and then the cross section area is delta y multiplied by 1. 1 is the unit width. And then from the top in the y direction we have flow, that is Vy multiplied by delta x times 1. And the flow that is exiting is given by the velocity, exit velocity multiplied by the cross section area in the x direction, and exit velocity in the y direction multiplied by the cross section area. So if you simplify this continuity equation, then you get this relation where dou v by dou x plus dou v by dou y equals to 0. So this is the continuity equation. Continuity equation in partial differential form. And then This is the Darcy's law, which says the flow rate so the Darcy's law is the flow rate is a function of hydraulic conductivity of the material and then the cross-sectional area multiplied by the hydraulic gradient. So dH is the head difference. Let's say the fluid is entering this medium and then exiting this medium. Then the flow rate is Q and the cross-sectional area is A. The hydraulic conductivity of this material is K. And dH is the head difference from upstream to downstream over a distance of dl. So dH by dl is the hydraulic gradient. So we have this Darcy's law which states that the flow rate is a function of K, hydraulic conductivity, area multiplied by the hydraulic gradient. So again, the flow rate is simply area times velocity, and that equals Kx, dH by dx, and Ax. We are constrained in the x direction. And if you simplify this, you get a relation for velocity dx, which is the function of hydraulic conductivity multiplied by the hydraulic gradient in x direction. And dH by dy is the hydraulic gradient in y direction. So you can get an expression for dy. Now earlier what we had was dou Vx by dou x plus dou Vy by dou y equals to 0. This was the continuity equation we had. Now if you replace Vx and Vy with these new terms, what you get is this. Which is dou square kx h by dou x square plus dou square ky h by dou y square equals to 0. And kx h or ky h or the velocity potential. So if you replace kx h and ky h by velocity potential, then what you get is the Laplace equation, which is dou square phi by dou x square plus dou square phi by dou y square equals to 0. So this is the Laplace equation for two-dimensional flows. And phi is the velocity potential, and it is a scalar. It does not have direction, so it has only magnitude. And if you differentiate the velocity potential with respect to x, you get the velocity in x direction. If you differentiate the velocity potential with respect to y, you get the velocity in that direction. So this is the Laplace equation and the velocity potential. Now, to analyze the flow through the seepage, or to analyze the seepage through earthen dams, we are going to make use of flow net. So the flow net is formed with flow lines and equipotential lines. Flow lines flow lines represent the path of particles of water through the saturated soil. So for example, here what I have is a flow net. So the red lines are flow lines. And the yellow are equipotential lines. So the flow lines represent the fluid path. So the fluid from upstream are going to travel to the downstream, and the path of the fluid is going to be along the red lines. So the path is going to be along the red lines. Whereas equipotential lines represent points where the head difference or the head gradient is identical. For example, if I consider a point here, here, here. So if I'm joining all these points, it means that the head difference is same along these points. So when I join all these points, then what I get is equipotential line. And usually the equipotential lines and flow lines intersect orthogonally, meaning the angle is going to be 90 degrees. So you would form small squares in the flow net. So these are all squares in the flow net. So again, flow net is formed with flow lines and equipotential lines, where flow lines represent the path of the fluid and equipotential lines are drawn by connecting points where the head difference is the same. Now, once you draw the flow net with flow lines and equipotential lines, then this region between two flow lines and two equipotential lines is called a field. So if you consider a square which is formed by two flow lines and two equipotential lines, that is called a field. Whereas if you consider two flow lines, then the portion in between these two lines is called channel. So the flow is going through the channel, so it is called flow channel. So we have flow channels and the field. Now let's say I consider one of the fields, which is a square, or it could be a rectangle. So let us start with assuming it is a rectangle which has a height of b and length L. Then what we are interested is to find out what is the flow rate through this each square. So what is the flow rate through this square, what is the flow rate through this square, and what is the flow rate through each of these squares. And since these elements are small, I represent the flow rate by delta Q. So the flow rate through each field is delta Q, and the total flow rate would be Q. And similarly, if the total head difference, let us say on the upstream we have a water level up to height h, on the downstream there is no tailwater, then the head difference is going to be h. So the total head difference is going to be h. But if I consider individual squares, then I would say the head drop would be delta h. So delta Q is the flow rate through each flow channel or each square, and then delta H is the head loss or the head drop from one equipotential line to another equipotential line. So let us say here we have a head H. By the time we come here, we might have lost delta H. So the head drop is delta H. Now for this square, if I apply Darcy's law, then the Darcy's law is Q equals K times dH by dx b times 1. So earlier what we have seen is Q equals to Ka dH by dN. This is the Darcy's law. Now since we are interested in a small elemental area, now I'm replacing Q with delta Q, and K remains the same. The area is B times 1, and then the head drop is delta H over a distance L. So this is the flow rate, delta Q equals to K times delta H by L multiplied by B. Now let us say there are, so let's say we have drawn a number of equipotential lines. So meaning the head starting from here has been dropping at every equipotential line. And let us say the total number of drops is ND. So ND is the total number of drops along the equipotential lines. So ND is the total number of drops. Then delta H would be H divided by ND. So we have total head, and then we know the number of drops. So each individual delta H for the small elements would be H by ND. And if you replace delta H with H by ND in the above equation, what you get is delta Q equals to K times H by ND multiplied by B by L. So this is the flow rate. If you know the total head, which is what generally we know. So generally, we would only know what is the water level on the upstream and what is the water level here, and we would not know the individual head drops. So then we make use of H and the number of drops and multiply with B by L. Now we have only looked at one individual channel. So there are a number of channels. So we have only looked at one channel. So if the total number of channels, this is 1, 2, 3, 4, 5. Let's say there are 5 number of channels. Then I call the total number of channels as NF. So the total discharge would be the above expression delta Q multiplied by NF. So the total discharge is delta Q multiplied by the number of channels NF. So if you substitute for delta Q, this is what you get. So the total discharge through the flow net is KH NF by ND multiplied by B by L. Now, as I said, generally we assume that the flow rate is square, then B equals to L, then you are eliminating this last term. So what you would get is this. So the flow rate through the flow net is KH NF by ND. So this is the total flow rate through the flow net. Now, the assumption that we made here is that the soil is isotropic. So what we assumed was the hydraulic conductivity in X equals to the hydraulic conductivity in Y. But what if the hydraulic conductivity is different? So if Kx is not equals to Ky, then we need to do the analysis again, since Kx and Ky are different. So this is our Laplace equation that we derived earlier. And in this Laplace equation, we have Kxh and Kyh. What I'm going to do is to introduce a new term Xn. So now I want to make sure that I eliminate Kx and Ky in this equation. Now to eliminate Kx and Ky, what I'm doing is to introduce Xn, which is x multiplied by square root of Ky by Kx. So I'm multiplying x with the factor Ky by Kx, so that I want to convert the Laplace equation from this form to something like dou square h by dou xn square plus dou square h by dou y square equals to 0. So this is what I'm trying to get to by utilizing this new term xn. So from the original equation, which is dou square kxh by dou x square plus dou square kyh by dou y square equals to 0, what I'm doing is to bring out ky. So if I take ky outside, then we have kx by ky here, because we do not have. So if I multiply ky with this factor, what I get is kx, which is originally there, and here I would get kx. Now this ky, whichever I have brought out, I'm going to send to the other side. So the Laplace equation would be kx by ky dou square h by dou x square plus dou square h by dou y square equals to 0. Now earlier what I have introduced is xn equals to x square root ky by kx. So my x square would be kx by ky multiplied by kn square. So if I introduce this in this term, then what you get is this. So this is again in the form of dou square h by dou x square plus dou square h by dou y square equals to 0. So we are trying to derive the same Laplace equation, but just we introduced a new term xn. Now to get the flow rate, so the flow rate is again delta Q is K times delta H by L multiplied by B times 1. But now this K is a new K. Earlier we had just used K since it is isotropic soil. Now the soil is anisotropic, so we have introduced a new hydraulic conductivity, which is K prime. And when we introduce this factor x equals to xn equals to x square root ky by kx, what we are also doing is to transform this square or a rectangle into a new transformation, so that we are multiplying L with the factor square root kx by ky. Since our x has changed to xn, we are multiplying L by this factor, because now we are talking in terms of the new x, which is xn. Now the L is L times square root kx by ky, and we have the new hydraulic conductivity for anisotropic soils, which is K prime multiplied by delta H by L times B equals to Kx delta H by L. We have introduced this. We are looking in x direction. And then the width B is going to be constant. So if you simplify this, what you get is the new hydraulic conductivity is square root of Kx Ky. So now we have find out the hydraulic conductivity for anisotropic soils. And now our delta Q is K prime times delta HL by B. We know what is K prime. So if you substitute that, you get K, square root of Kx K by H and NF by ND, which becomes the total discharge. So this becomes the total discharge through flow net. And this is for anisotropic soils. So now we have expressions for the total discharge through a flow net, whether it is isotropic or anisotropic soils. And then what we are going to do next is to identify the seepage line through the embankment. So earlier what we did was to calculate the flow rate through the flow net. Now what we are going to do is to identify where the seepage line is going to exit the dam, because we want to keep or make sure that the seepage line or the phreatic line is well within the downstream phase. We do not want it to cut through the downstream phase. Now, the first method is Casagrande's method, and in this method, the assumption is that the seepage line is a parabola. So if you look at the shape of the seepage line, so we have the embankment, and upstream we have some water, and let's say that in the downstream there is no water. So the seepage is going to start at point P, and then it's going to exit at the filter. So what we have in here is the filter. So this is going to drain the water, whatever is seeping through the embankment. Now, this shape is assumed to be parabolic. And based on this assumption, we are going to calculate the point where, or we are going to identify at this point where the seepage line is going to exit the dam. And also the assumption here is the filter is starting here, and the point is F, or the focus of the parabola. So the assumption is that the focus of the parabola F lies at the beginning of the drainage filter. So in this method, what we do is first, so we have the upstream phase, which is AB. So we have notations of different points, A, B, C, and D is here, and then E is at the exit, F is the focus, H, and G. So G is the point where the seepage line is exiting the Earthen dam. So first we know AB is the upstream phase, and we would also, based on the design of the Earthen dam, we would also know the length of the phase AB. So when you design the dam, you design it to certain slope, and based on the slope and the height, you can calculate what is the length AB. Now, we assume that the starting point of the parabola is at point C, which is at a distance of 0.3 times the length. So the assumption is that the starting point of the parabola is at point C, which is at a distance of 0.3 times the length L from point B. So now you can see this forms a parabola until G. So starting from C, the parabola ends at G. Now, once you identify the point C, which is at a distance of 0.3 times the length, now what we do is, with the point C as the center and CF, F is the focus of the parabola. So with C as the center and CF as the radius, you draw an arc, so which is represented by this pencil line. So you draw an arc and see where this arc intersects the vertical line. So you draw an arc and then you see where this arc intersects this horizontal line CB. Sorry. So we know CB, it's just horizontal line, so you extend CB. And then when you draw the arc, you know where the arc is going to intersect the horizontal line. Then that point becomes our point D. So if you draw a line, vertical line, HD, that becomes the directrix of parabola. Now we have identified the directrix of the parabola. Now the seepage line where it is exiting in the filter is denoted by point G, and this point G on the parabola is going to be equidistant. So this point is equidistant from both the focus and also the directrix. So G is going to be equidistant from focus and the directrix. So now we know what is point G, and we also have the point H where the directrix is, and we know point C where the parabola is starting. And based on the parabola properties, you can plot the parabola by identifying points. So if you keep identifying the points along the parabola, then you get a set of points, and if you join them, that becomes your parabola of the seepage line. So now you have the parabola, but the seepage line is not going to be at C practically. So C is only a theoretical point, but practically the parabola or the seepage line is going to start at point B. So once you draw this parabola, you need to adjust and then make sure that the seepage line starts at point B. So these are the different steps that you follow to draw the seepage line. And this is assuming that we have a filter in the dam and the focus of the parabola is at the starting point of the filter in the dam. Now let us look at this scenario where we do not have any filter, but still we want to identify the seepage line, where the seepage line is going to exit the dam in the downstream side. Now, what we do is again assume, begin with the parabola. So let us say the focus F of the parabola is at the toe of the dam, represented by F. And if the red line, the solid line, is the actual seepage, so the seepage is going to exit at point K. But what we assume is a parabola, so the parabola is exiting at point J. So the original seepage line is at K, but the theoretical seepage line is at J. So the distance JK is delta A. And then the distance from K to F, which is the distance from focus, is denoted by A. And the angle of the downstream slope is alpha. And from J, if you draw a vertical line, I would denote that as J naught. So now what we need to find is this correction factor. So earlier we have seen how to draw a parabola. So we assume the focus of the parabola is here, and then you would have a point C. So starting from C to F as a radius, you draw an arc, and then you identify the directrix. So once you identify the directrix and point C, then you start constructing the parabola. So you draw this parabola based on the earlier method, and then we need to now find out the offset delta A, because we do not know what is the practical seepage line exit point. So if we find out this ratio delta A divided by A plus delta A, then we can find out JK. So what we do is to find out JF first. So this is J is a point on the parabola, and F is the focus of the parabola. And we have a point that sits on the vertical line from J. So according to the parabola properties, your JF would equal J naught H. And J naught H is J naught F plus FH. So which is given by A plus delta A. So your JF is A plus delta A, and that equals J naught H, and that is given by two parts, which is J naught F plus FH. And J naught F you can calculate based on this angle, so you know the angle, and then you know the distance from JF. So JF cos alpha plus S would be your JF. So we are simply modifying this J naught F into JF and making use of the angle cos alpha. Now if you simplify this, what you get is JF is S by 1 minus cos alpha. So alpha is known when you design the dam. So you know alpha because when you design the dam, you choose the side slopes for upstream and downstream. And then S would be the distance from the focus to the directrix. So this comes from the parabola. So now you have JF, which is equals to S by 1 minus cos alpha. Now once you know JF, then you need to calculate what is delta A because we are interested in JK. So JK is delta A, and we have one more equation from Casagrande's method where the relationship between the angle alpha and delta A by A plus delta A is known. So this comes from experimental data. So based on experimental data, we have a relation for delta A by A plus delta A and alpha. So you know A by delta A by A plus delta A is some constant from alpha, and then you calculated JF again, which is A plus delta A. So you have two equations and two unknowns. So we have calculated JF earlier, and now we have another equation based on alpha. So you have these two equations, and the two unknowns are A plus delta A. So if you solve for this, then you can calculate what is A and what is delta A. So this is how you identify the C phase line where it exits the downstream phase. Now, let's take a step back and see. Let's look at this dam where we have a filter, and then we have identified the seepage line. Now we need to find out what is the discharge through this seepage line, or what is the discharge through this entire seepage. So you have seepage all across here of the dam. So we need to find out what is the discharge through this. So to do that, what we do is again make use of the parabola equation. So here is my point P on the parabola, and then we have F, G, H, and Q. So the point Q is down here. So we have points P, Q, F, G, H. Now PF or PF, which is from distance, the distance between point P to the focus F, would equal QH. So PF equals QH. So PF you can calculate as square root of x squared plus y squared. Since let's say if I say this height is y and the distance is x from the focus point, so PF would be square root of x squared plus y squared. And then QH can be two components, which is QF plus FH. So that becomes x plus s. Now, if you rearrange this, you get an expression for y squared, which is the equation of this parabola. And to find out what is the discharge through this parabola, we again make use of Darcy's law. So Darcy's law is K times dH by L times A. So here the head dH is dy, the length L is dx, and the area is y times 1. So replacing dy with this y, since we have an expression for y, so you can replace this y with this x and s. And if you simplify this, you would get a relation for the flow rate or the discharge. So now we know the flow rate or the discharge through the seepage line. So to summarize the concepts that we have seen today, the first thing what we did was to derive Laplace equation. So once we derived Laplace equation, what we did was to get the flow rate or so we learned the concept of flow nets, and then we derived flow rate through flow nets. And then what we did was identify seepage line. Using Casagrande method. And then we also identified seepage line when there is no filter. And then we derived flow rate through the embankment. And when we derived the flow rate through flow nets, we also did isotropic soils and anisotropic soils. So this is the summary of the concepts that we did today. So in the next lecture, we are going to do the stability analysis of the embankment dams. And once we finish the stability analysis, we are going to move on to spill rates. So any questions on this today? I'm going to upload the notes and the recording. Are there any questions? All right, so I'm going to upload the solutions for the tutorial questions 1 to 4 as well, right after the class. And the lecture notes and the recording will be available as usual. So if there are no questions, then I'm gonna close the session. All right, so I'm going to close the session now. Thank you. And you can write to me if you have any questions. Get in touch with me and we can discuss. Thank you.